when you are streaming music, downloading a huge file, and, I don't know, typing an email all at the exact same time, your computer is basically lying to you.
Oh, completely. It's a total fabrication.
Right. Because it isn't actually doing all those things at once.
Yeah.
It is, well, it's performing one of the greatest, most seamless illusions in modern engineering.
It really is an illusion, and, we fall for it every single day. We just expect our devices to be these, infinite multitaskers.
We do. We take it for granted.
Yeah, but at a microscopic level, the reality of how a computer manages its workload and how it keeps from just instantly crashing is so much more fascinating than just, doing it all at once.
And that illusion is exactly what we are tearing down today. Welcome to today's deep dive.
Thanks for having me. I'm excited for this one.
So we are pulling apart a really fantastic academic text today. It's excerpts from Information Systems for Managers, which is published by IGNOU, the People's University.
A really solid foundational text.
Yeah, it is. And the mission here is to decode the invisible architecture running our digital lives.
Yeah.
We're going beyond just, pointing at the screen and saying, oh, that's software.
Right, because that doesn't really tell you anything.
Exactly. We want to look at the mechanics. How does a microchip actually understand human intent? And, if you are managing a business or even just managing your own digital life, how do you make smart decisions about the tools you actually rely on?
It's a crucial transition in understanding technology. I mean, most of us just think of the applications we interact with, like the web browser or the photo editor.
Right, the stuff we actually click on.
Yeah, but this text forces us to look a layer deeper at the absolute fundamental division in all software, which is system software versus application software.
Okay, let's unpack this, because before an application can even exist, something has to, pave the roads and build the infrastructure, right?
That's exactly it. Think of system software as the ultimate low-level mediator.
The mediator between what and what?
Between you and the physical machine. I mean, your physical computer, the processor, the memory chips, the hard drive, it speaks purely in electrical impulses.
Just raw voltages.
Right. And your application software, say a massive video game, is this huge bundle of high-level code. So the system software sits squarely between them. It is the environment that actually allows the applications to run.
And the absolute heart of that environment is the operating system, right?
Yeah.
Like Windows, Mac OS, Linux.
Precisely. And within the operating system, the text points out that the most critical operations are handled by a component called the kernel.
The kernel. So what is the kernel actually doing mechanically?
Yeah. So the kernel is essentially the air traffic controller for the physical hardware. When you boot up your computer, the kernel is the very first thing loaded into memory.
Oh, wow. First thing.
Yeah. And it controls the absolute most sensitive interactions. Things like which program gets access to the processor, how memory is handed out, and how the computer talks to physical devices like a printer or a keyboard.
It's doing all the heavy lifting in the background.
Exactly. If the kernel fails, the entire machine just halts. It is the pulse of the system.
But the OS isn't just a hidden traffic controller. It's
Yeah.
also providing the face of the computer, the user interface.
Right, the part we actually see.
Yeah. And the source material spent some time on the evolution here. It is a pretty stark reminder of how far we've come. I mean, it mentions Job Control Language, or JCL.
Oh, JCL, yes, the early days of command-based systems. I mean, imagine staring at a completely blank black screen.
No, thank you.
Right. There are no folders to click. There is no little trash can icon. If you wanted to delete a file containing, say, your tax return, you couldn't just drag it somewhere.
You actually had to memorize commands.
You had to memorize and type a specific syntax, something like erase tax RTN.
Which requires the user to adapt to the machine, rather than the machine adapting to the user.
Exactly the problem.
Yeah.
And that is why the shift to the graphical user interface, the GUI, was just so revolutionary. The text highlights the pioneers at Xerox PRRC, that's the Palo Alto Research Center out in California.
Right. They were the ones who really dug into spatial reasoning for computers, didn't they?
They did. They investigated the idea of overlapping windows and those little visual icons.
Because they realized humans understand the world visually by actually manipulating objects. So they basically built a digital desk.
Yeah, exactly, a digital desk. Which, of course, paved the way for Microsoft Windows and Apple's operating systems later on.
And while the OS is busy providing that friendly visual interface for you, it is simultaneously providing a completely different, but equally vital interface for software developers.
Yes, the APIs, application program interfaces.
Okay, I want to dig into APIs, because the text says they provide hardware independence. Let's ground this for a second.
Sure.
Wait, if a computer manufacturer makes a brand new lightning-fast microchip tomorrow, why doesn't an app developer have to completely rewrite their app to work on it? Why doesn't Spotify or Word just instantly break?
What's fascinating here is that the application developers don't ever actually talk to the microchip.
They don't.
No, they talk to the API.
So they just hand the request to the operating system.
Essentially, yes. The API is basically a standardized menu of commands. When a developer writes an application, they aren't writing code that says, send this specific voltage to this exact microscopic sector of the silicon.
That would be impossible to maintain.
It would be a nightmare. Instead, they write code that says to the OS, please draw a window on the screen, or please play this audio file.
And then the OS takes over.
Right. The operating system is the one burdened with learning how to actually communicate with the new hardware.
So system software is like the stage crew in a theater, and application software are the actors.
Oh, I like that.
Yeah, you pay to see the actors, but without the crew managing the lights and the curtains and the sound, the show just doesn't happen. The API acts as a universal translator.
That's a great way to put it. The app asks for a standard favor, and the OS figures out how to execute it on whatever physical hardware happens to be in that specific machine.
Which totally explains how tech can innovate so fast on the hardware side without destroying the entire software ecosystem every single year.
Exactly. It abstracts all that messy complexity away from the developer. But I will say, managing those requests from all those different apps requires an unbelievable amount of coordination, especially when it comes to memory.
Well, let's transition into that juggling act.
Yeah.
Because the OS is managing all this hardware, so how does it juggle the demands? The text talks about memory management, specifically how the OS converts logical views of data into physical locations.
Yes, this is a big one.
What does a logical view actually mean in this context?
Okay, so when you open a document, you have a logical view of it. You just think of it as quarterly report.pdf sitting peacefully in your documents folder.
Right. That's how my brain organizes it.
But the computer hardware doesn't know what a folder is. It only knows physical addresses, literally microscopic gates on a piece of silicon. So the OS's memory controller has to instantly translate your logical request for that PDF into a map of scattered physical locations all across the memory chip. It pulls them all together and presents them to you seamlessly.
And it has to do this while keeping all the different applications from bumping into each other and crashing the whole system.
Yeah, and that's where the security comes in. The text mentions the OS uses rings of protection on the computer chips.
Rings of protection. How does that work?
It is a brilliant security mechanism built right into modern processors. Imagine a target with concentric circles.
Okay, got it.
The innermost circle, ring 0, has total unrestricted access to all the hardware. That is where our air traffic controller, the kernel, lives.
Okay, and the outer rings.
The outer rings, like ring 3, have highly restricted access. That is where your web browser and your video games live.
So they are kept far away from the core machinery.
Exactly. And the OS enforces this quarantine mechanically. If your web browser, encounters a bug and tries to execute a command that would overwrite critical system memory, the hardware physically checks its privilege level.
It actually checks its ID,
yes.
basically.
It sees the browser is stuck in ring 3, denies the request, and just crashes the app instead of taking down the entire operating system.
So it's a structural quarantine. That makes a lot of sense. Now, what happens when all of these quarantined apps start demanding too much memory? We all know short-term memory, RAM, is pretty limited.
It is very limited, yeah.
The text explains that when the OS runs out of RAM, it turns to virtual memory. Walk us through this mechanism. It's called paging, right?
Yes, paging.
Yeah.
So think of RAM as a very small, very fast desk where you are actively working on some documents.
Okay.
Your hard drive is a massive filing cabinet sitting all the way across the room. Paging is what happens when your desk gets completely covered and full.
I know that feeling.
Right. The OS basically looks at the desk and says, well, you haven't looked at this spreadsheet for 10 minutes. So it grabs that spreadsheet out of RAM and temporarily swaps it over to the hard disk.
Just to clear physical space on the desk for whatever I'm doing right now?
Yeah, so the processor doesn't just stall out and freeze. Then the second you click back on that spreadsheet, the OS rapidly pages it back from the hard drive to the RAM. And it might say, swap out your email app to make room for it.
It's like playing a high-speed shell game with your data.
A very, very fast shell game, yeah.
Which brings us right back to that multitasking illusion we started with at the beginning of the deep dive. We ask the OS to juggle our memory, but we also ask it to juggle time.
Time is the tricky part.
Yeah, and the text distinguishes between time sharing, which is like multiple users on one system. Think of thousands of customer service reps hitting a database, and multitasking, which is one user running multiple apps on a laptop.
Right, slightly different scenarios, same core illusion.
So I want to push on this multitasking illusion. Here's where it gets really interesting. When I'm streaming music and I'm writing a document,
Yeah.
you're saying the computer isn't actually doing both at the exact same millisecond.
Assuming we are talking about a single processor core, no, it is absolutely not. It is doing one single thing at a time.
Really?
Yeah. The CPU divides its time into tiny microscopic slivers called time slices.
Wait, if it's literally stopping my music player to go process the keystroke I just made in my Word document, why don't I hear a stutter or a gap in the audio?
Because of buffering and just sheer incomprehensible speed. I mean, a time slice is measured in milliseconds or even nanoseconds.
So it's unfathomably fast.
Exactly. The CPU processes a tiny chunk of your audio, hands it to the sound card, instantly abandons the music player, jumps over to the word processor, registers the letter you just typed, draws it on the screen, and then jumps back to the music player before the sound card has even finished playing that last tiny chunk of audio.
Wow, so it's jumping back and forth so rapidly that human biology simply can't detect the gap.
That's it. It's like a flip book. You have individual static images moving so fast, your brain just perceives continuous motion.
Right.
Whether it's multitasking on your laptop or time sharing on a global server, dealing with thousands of users, it's just slicing time into tiny pieces.
Okay, so if the operating system is managing time slices at the nanosecond level and juggling physical memory locations on tiny pieces of silicon, how on earth does a human programmer actually tell it what to do?
That is the ultimate challenge.
Because the human brain works in concepts and logic, not binary ones and zeros.
Yeah,
That takes us into the language barrier.
right. The CPU only naturally speaks machine language, binary digits, literally just on and off space. To bridge the massive gap between human thought and binary execution, we rely on language translators.
Which actually fall under the umbrella of system software, according to the text.
They do, yes. They are part of that foundational layer.
And the text highlights two dominant types of translators for programming languages, compilers and interpreters. Let's break down the mechanical difference here.
Okay, think of building a complex piece of furniture. An interpreter is like having someone read the instruction manual to you step by step while you build.
Like a live translator.
Exactly. They translate line 1, you execute line 1. They translate line 2, you execute line 2. It's translating on the fly.
Which implies it's a bit slower, because you have to literally wait for the translation of every single step as you go.
It is inherently slower, but the massive advantage is flexibility. You can take that source code to a Windows machine, a Mac, or a Linux server, and as long as that machine has an interpreter installed, it will read the code and run it.
Okay, so how does a compiler change that dynamic? Is a compiler like translating an entire French novel into English before publishing it, whereas an interpreter is like having a live UN translator whispering in your ear sentence by sentence?
That is a perfect analogy, yes. A compiler is like someone reading the entire instruction manual, translating the whole thing into your native language, printing it as a brand new book, and handing it to you.
So you don't need the translator in the room anymore.
Right. The compiler takes the entire high-level source code, translates it all into machine code up front, and creates a finished executable file.
And because the translation is already finished, a compiled program must execute incredibly fast.
Incredibly fast. The trade-off, though, is that the compiled file is heavily tied to the specific operating system it was compiled for.
Ah, so you lose the flexibility. Although the text does note that some languages try to cheat this system. Java, for example, is a hybrid.
Java's very clever.
It compiles the code halfway into something called bytecode and then uses a virtual machine to interpret that bytecode on the fly. It's basically aiming for the speed of a compiler with the portability of an interpreter.
It's a great compromise. And the languages themselves have evolved drastically alongside these translators. The text traces this evolution through distinct generations.
Let's run through those. The first generation was just raw binary, right?
Mhm.
Machine code.
Which is brutally unforgiving. 1 0 out of place, and the whole thing crashes. So programmers created second-generation languages, which was assembly language.
And that introduced mnemonics.
Right. Instead of typing a huge string of binary just to subtract a number, you could finally type SB.
But you still had to understand the deep physical architecture of the specific machine you were programming. You were still essentially telling the computer exactly how to move data between physical registers.
Yeah, it was still very low level, which is why the third-generation languages, the 3GLs, were such a massive boom. These finally introduced English-like keywords and mathematical formulas.
The text mentions a few of these. The 1950s through the 70s gave us Fortran for science, COBOL for business, BASIC for beginners.
And Pascal as well.
The text also specifically calls out the C language, developed in 1972 at Bell Labs by Dennis Ritchie, noting its enduring popularity for writing system software. Why C? I mean, with all the newer languages we have, why is a language from the 70s still used to write operating systems?
Because C offers a very rare combination. It provides the structured, high-level English syntax that makes it easy for humans to read, but it also allows the programmer to directly manipulate individual bits of memory.
Which most modern languages don't let you do.
Right. Most modern languages hide the memory management from the programmer to prevent errors. C gives you the keys to the kingdom. If you are writing an operating system, you absolutely need that granular, dangerous level of control over the hardware.
You need to be able to talk directly to the physical disk, not just the folders.
Exactly. But for application developers, we kept abstracting. We moved to fourth-generation languages, 4GLs. These are categorized as non-procedural.
Procedural meaning you have to tell the computer every single step of the process. So non-procedural means what? Exactly.
It means you only focus on the output. You don't tell the computer how to do the task, you just tell it what you want.
Oh, I see.
SQL, which is used for managing databases, is the perfect example. You write a query that essentially says, give me a list of all customers in Ohio who bought a product last week.
You don't write the instructions for how the database should physically search its hard drives or sort the data?
Nope. The 4GL translator figures out the procedure for you.
That's a huge leap in usability. The text also emphasizes object-oriented programming, or OOP, with languages like C++ and Java. Let's dig into the mechanics of this, because it revolutionized how software is built.
It really did.
How is OOP different from the previous generations?
Well, before OOP, code was generally written as a long top-to-bottom list of actions. You had your data in one place, and the functions that acted on that data in another entirely separate place.
It sounds like it could become incredibly tangled.
Spaghetti code, they called it. Object-oriented programming completely flipped the script. It bundles data and the functions that operate on that data together into a single, self-contained unit called an object.
Give me a real-world analog for that.
Imagine you are programming a simulation of a city. In the old way, you'd have massive separate lists of data for every single vehicle and massive separate lists of functions for how they move.
Right.
In OOP, you create a blueprint called a class for a generic vehicle. That blueprint contains data like speed and color and functions like accelerate and brake.
Okay, so that's the generic template.
Right. And here is the magic mechanism. Inheritance.
Inheritance.
Yeah. You can now create a new class called ambulance that automatically inherits everything from vehicle, but you just add a new specific function for turn on siren. You don't have to rewrite the code for accelerating or braking.
Oh, wow. It just takes it from the parent class.
Exactly. It makes massive software projects modular, reusable, and infinitely easier to troubleshoot.
Speaking of massively popular languages, the text covers Python. And it drops a really fantastic piece of trivia about its creator, Guido van Rossum, developing it in the late 80s and early 90s.
Yes, this is a fun fact. Despite the logo being a snake, the language has nothing to do with reptiles.
Right.
Van Rossum was reading the published scripts of the 1970s British comedy series, Monty Python's Flying Circus. He wanted a name that was short, slightly mysterious, and unique.
I just love that one of the foundational pillars of modern artificial intelligence and data science is named after a sketch comedy troupe.
It adds a nice bit of humanity to the code, doesn't it?
It really does. So we've covered the deep architecture. We have the OS juggling memory and time slices, and we have programming languages translating human intent into binary. But let's bring this down to the consumer level.
The practical application.
Yeah, because if you are a business manager or just someone trying to run a project, you don't care about the kernel. You just need application software, the tools that actually do the work.
Right. You need a word processor, a CRM system, or virtual conferencing tools like, say, Melancetu or Zoom. And the text breaks down how organizations actually acquire these tools into a classic dilemma: build versus buy.
Which seems straightforward on the surface. I mean, if you have highly specialized needs, say you run a hyper-specific logistics network, and you have software engineers on payroll, you build it in-house.
Or you contract a vendor to build it custom for you.
Right. But building is expensive, time-consuming, and risky. So if your needs are standard like payroll or email, you just buy off the shelf standard packaging.
Exactly. But the text introduces a third pathway that has profoundly disrupted the traditional proprietary software market.
And that is open source software, or OSS.
Yes, often called FOSS or FLOSS. Open source operates under licenses like the General Public License, MIT, or Apache.
So what does this all mean for the consumer?
Well, the defining characteristic is that the original source code is distributed right alongside the software, entirely for free.
Anyone can look at the blueprints, modify them, and redistribute them.
Exactly. It is a radical departure from companies that guard their proprietary source code like it's, the Coca-Cola recipe.
I want to push back on this heavily on behalf of any manager listening, because if I am a hospital administrator or a bank manager, security is my absolute #1 priority.
Absolutely.
So if open source software literally posts its foundational blueprints on the internet for anyone to read, why on earth would I use it? Doesn't that just give hackers a free map to find every single vulnerability?
It sounds incredibly counterintuitive, I know. But if we connect this to the bigger picture, the mechanical reality of how software development works makes open source highly secure.
Really?
It relies on a concept often referred to in tech as Linus's law. Given enough eyeballs, all bugs are shallow.
Meaning what exactly?
Well, imagine a proprietary software company. They have a closed security team of, maybe 50 engineers looking for flaws.
Right.
When a bug is found, you are entirely at the mercy of that specific vendor's timeline to fix it. Now, look at a major open source project. You have a global army of potentially tens of thousands of developers, researchers, and users scrutinizing that code every single day.
So the sheer volume of independent audits outweighs the risk of the blueprint being public.
Precisely. When a vulnerability is found in a major open source project, a community developer often patches it within hours, long before a malicious actor can exploit it at scale.
Because they're highly motivated to fix the tools they actually use.
Exactly. You aren't relying on one company's internal priorities or profit margins.
Yeah.
You are relying on a massive decentralized network of experts. It provides immense security, transparency, and it avoids vendor lock-in.
The transparency is the security. You don't have to just blindly trust that a vendor wrote good code. Your own engineers can literally inspect it line by line.
And you can modify it to fit your exact infrastructure without asking for permission.
We have unpacked a tremendous amount of architecture today. I mean, we started all the way at the bottom, looking at how the operating system's kernel acts as the air traffic controller.
A lot of hidden mechanics.
We looked at rings of protection and virtual memory paging, keeping the machine from collapsing. We explored the illusion of time slicing that makes multitasking even possible.
The great flip book.
Yeah. And then we walked through how interpreters, compilers translate human logic into binary, how object-oriented programming revolutionized how we organize that logic, and finally, how the open source movement leverages global transparency to create secure applications.
It is a beautifully complex ecosystem, but, understanding these underlying mechanics changes how you view every single interaction you have with a screen.
It really does.
And to that end, there is a concept from today's text that I think is really worth dwelling on as we wrap up.
Oh, let's hear it.
So we talked about fourth-generation languages, those 4GLs, the non-procedural tools where the programmer doesn't write the steps, they just demand the output, like, get me this data.
Right, focusing purely on what you want, not how the computer gets it.
Well, if the trajectory of programming has moved from toggling physical hardware switches to typing binary to using English keywords to simply demanding an output, consider where we are right now with natural language processing and AI.
Oh, wow. I see where you're going with this.
Right. At what point does the line between using an application and programming a computer just disappear entirely?
If you could just type a plain English sentence into a prompt, and the machine figures out the complex procedure to execute it.
Are we fast approaching a future where simply asking your computer a question makes you a programmer?
It completely reframes the search bar on my phone. We are moving from giving commands to just having a conversation with a machine. The compiler of the future might just be listening to us talk.
The architecture is already in place. The system software is just waiting for the instruction.
What a phenomenal thought to leave on. Thank you for joining us on this deep dive. And for you listening, You are now armed with the mechanical understanding to look past the illuminated glass, recognize the illusions keeping it all running, and be a fundamentally smarter consumer of the technology you interact with every single day. We'll catch you on the next one.